Welcome back to another LeetCode video. Today we're continuing our quest in the graph section of LeetCode.io's curated list of graph problems. We're going to look at a redundant connection today. Right, so redundant connection is another graph problem. Let's just read through it and then let's solve it. In this problem, a tree is an undirected graph that is connected and has no cycles. We are given a graph that started as a tree with n nodes labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge that already existed. The graph is represented as an array of edges of the length n, where each edge has two nodes in them, indicating that there's an edge between these two nodes. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs last in the input. Right, so let's have a look at these examples in the drawing board. There you go. And, wrong place. And insert it again. Okay, cool. So like this, right. So, okay, so we have a tree and then an edge was added. And theoretically, we could remove any edge to make it a tree again, but we are supposed to return the last edge that is on the cycle in the graph, right? So here, this is the edge between 2 and 3. In the example below, well, again, we have 4 different candidates for the edges. However, we need to return the last one that was added to the graph. So the first added was 1 to 2, so this was the first one. 2 to 3 was the second. 3 to 4 was the third. 1 to 4 was the fourth. And 1 to 5 was the fifth edge that was added. So we actually have to remove this edge here. Now, if you were to construct this, I mean, we're given a list of edges, right? So it's clear that in order to traverse this graph, we kind of have to create a graph object. And we're going to use a dictionary again that is basically where the key is the source edge, and then it has a list of so the source edge, and then has a list of basically adjacent nodes, right? U1, U2, etc., etc., etc. And if we were to construct this graph in one go and then try to find the cycle, it would overcomplicate things quite a bit for us. We would then have to figure out, okay, which one was the edge that was added last? And furthermore, we would have to figure out, if the graph contains more elements, maybe that are not on the edge, 5 that are not on the cycle, right? Something like that. We would have to identify the cycle, not just that there exists a cycle, but we would actually have to identify the nodes that are on the cycle. And then we would have to identify the edge that was last added. So that would be extra steps. I think we could make it easier for us if we just take the hints from the problem description, where we are given a graph that started as a tree, and then the additional edge was added. So if we start to construct our tree in the same order that we're given the edges, once we identify that there is now a cycle when we add this edge, we have found our edge. So what we could do is while we construct the tree, we're going to check if there's an edge between the two edges that we're trying, between the two nodes of the edge that we're trying to add. So before we add the edge between 2 and 3, we're actually going to check, oops, wrong color. We're actually going to check, is there a cycle from 3 to 2? So can we already reach that node? And if that's the case, then this is going to be our return edge. So that seems pretty straightforward. And we're going to go into the runtime analysis in a little bit. And I'm just going to put the template text here for time and or of something space. And well, how do we start? Well, we need to construct our tree. So we're going to let's use a default So we don't have to mess with creating lists when the edge is not yet existent in the graph. And we're just going to iterate over all of the edges that we're given. So for edge in edges. And well, what do we do? Well, we need the source and the destination node from the edge. So let's just pull that out. And now we would have to check if can reach the destination from the source. If we can do that, then that means we found our edge. Return edge. That's exactly the same logic that I just described when we looked at the problem. And otherwise, if this edge doesn't add a cycle, well, obviously we're going to add that edge to our graph. So source.append destination, but since it's an undirected graph, we also add the edge in the other direction. Right. Cool. And then in the end, well, what should we return if there's nothing? Well, there's nothing else to return, so we actually don't have to do anything. It's guaranteed that there's going to be a cycle, and it's guaranteed that we will return an edge. So we don't really have to do anything below here, even though that feels a little weird. So now we need to implement our canReach method, right? And well, that's going to be an expensive one, because we're going to have we're going to put in a node and a target node. And well, we should return whether we can reach an edge. How can we do that? Well, we can use a breadth-first search to try to traverse through the existing graph to find it, or we could just use a recursive search using DFS instead of BFS, so depth-first search. And yeah, this, of course, is going to be an expensive operation, because depending on how many edges we already have in our graph, we're potentially going to visit all of the edges in the worst case. So this solution that I'm showing you is not, there's a faster one, but this one is, I guess, a really easy one conceptually and easy to implement. And if you were to come up with this one in an interview, I think that would be very good. And maybe then the follow-up question is, how can you optimize that? But yeah, let's look into this before we do any optimization. So what we do is we check if node is equal to target, right? Well, then we're done, and we just return true. Because that means, well, we can reach target from the node. And if it's not the case, well, then we need to start visiting our neighbors. So for neighbor in, well, the neighbors of that node, right? And maybe there are no neighbors, then there's nothing to do. But maybe there are neighbors, so we have to visit them. So if neighbor, right, if path, no wait, if can reach, if there's a path from the neighbor to the target, then we also return true. And otherwise, we return false. Now, the sharp observer will notice that this will result in an infinite loop, because we're not checking if we've already visited a node before, right? We might be going back and forth between two nodes indefinitely, and then we run into out of heap error or something. So we need to keep track of all the nodes that we've visited. So we're going to need a visited set. And let's see. Well, we need to pass this visited set between a recursive calls. So we have to add this to our parameter list. And we also have to set an empty set in the beginning, because we're starting a new depth-first search every time we call reach. We don't have to remember the set after we finish the canReach method. So now we're passing that in. And if, well, we also have to check, if a node is already invisited. So what we would do here is, well, we can either check here, if node invisited, return false, or we do it right here. If neighbor invisited, continue. We're just going to ignore that. We're not going to revisit neighbors that we've already visited. And that is everything there is to it. Let's just run the test to make sure we don't have any syntax errors in here. And while our two test cases pass, that's a good sign. Now let's have a look at the space and time complexity analysis. So obviously we're iterating over all of the edges. So our first component would be the number of edges. in the input. Then we have to multiply that with whatever the complexities of our can reach method. Well, at every iteration of the edges loop, our graph grows by another edge. So in the kth iteration, can reach, in the worst case, traverses through k edges, right? So that means we're actually going to, well, not only does it traverse through all the edges, but also through all the nodes that we've added to our graph. So in the worst case, it would be number of edges plus number of vertices. In space, and you can simplify this, this would be the number of edges squared, and edges times vertices is always going to be less than edges squared because it's a fully connected graph, so that means we always have more edges than vertices. So O of edges squared is the upper bound for the, or the tight upper bound for the time complexity to run through this algorithm. And in terms of space, well, we're constructing the entire graph. So here we actually have to, well, we're going to store number of edges and number of vertices because we're adding them to our own little graph structure here. And yeah, let's now submit this. And it works, so that's very nice. Yeah, I hope you enjoyed this one. Turns out this is a really simple one if you consider, that you actually can perform the has a cycle check doing the construction of the graph, which is something that we haven't seen before. Before in the other problems, we've only seen, constructing the graph and then performing checks, etc. So in this one, that's a new little trick that we should remember.